So one of the great mysteries that physicists had to try to explain, which made no sense, is something known as the photoelectric effect. So here's the best analogy that I can give you, is that basically what the photoelectric effect is that if you have a metal, and if you shine a light on the metal, and if the metal has, or if the light has enough energy, then it will take one of those electrons that's orbiting towards the outside and knock that off, okay? And then that creates a current, and then that's how you know that this is happening. So you can kind of make the analogy that, let's say hypothetically, that Nathan Nelson ends up in jail.
Hypothetically?
Let's just say hypothetically.
Bro, only
Insider trading, something. Okay?
Oh, shit.
I can see even that.
He got me.
I'm just saying, hypothetically, you're in jail.
Hypothetical. Yep.
And Nathan goes, man, I got to get out of jail. Let me call up Burke. Okay? So Nathan calls me up and he says,
Pay my
hey,
bill.
Burke, can you help a brother out? I said, what's your bail set at? He goes, it's only $500.
Oh, that's not bad.
It's not bad. So the bond, this is why this is free bailiff, okay? This is from this story, okay? So instead of bailiff, Nathan is in jail, okay? So this is like free Nathan. So let's say I show up and his bail is set at $500. And I go to the judge and I say, hey, I got $490. Don't have $500. What's going to happen?
You should take a loan.
Okay? The judge is going to say, you got nothing. Now, if I show up at exactly $500, I can get Nathan out of jail. But now I don't have any money left over to pay for the Uber ride home or go to McDonald's and get some McNuggets or something. Okay?
But you got a big name.
But I got him out of jail,
I got you, man.
but we're basically stuck at the jail because there's nothing left over.
I'll take his
Okay.
donations.
Now, I show up with 6 Huskies, okay?
Wheat is good, bro.
So I got to pay $500 to get him out of jail, but now we're left with $100 left over to have some kinetic energy. Okay?
Have some arguments.
However, you can find that buys a lot of arguments.
Yeah.
Okay? So here's where light becomes a part of the story. So here's this Joe electron orbiting around the nucleus, and it's minding its own business. It's bound up. It's creating the solid. Okay, right? Doesn't let other electrons in. It's minding its own business. So along comes this light, and it has to have a certain amount of energy. If it doesn't give it enough energy, that's like me showing up to get Nelson out of jail without enough money. The judge is going to go, hey, I appreciate the fact that you're a teacher and you have the best of intentions, but we're not letting you out of jail. So if you look at this equation for the photoelectric effect, this is K max, which is your maximum kinetic energy, equals HF. Now, the HF part of this comes from the energy of light. Okay? So all that is the energy of a photon of light. This is equivalent to how much money I have. Okay? So the HF part of it is Burkheim. Okay? This Greek letter phi is what we call the work function. The work function is how much bail the judge set to get Nathan out of jail. Okay? So, if his bond is set at $500 and I show up with $490, nothing's going to happen. So I can't plead my case and go, hey, he's a nice guy, I'll vouch for him. The judge is going to say, appreciate the effort, not going to happen. And this is going to be important. No matter how much time I spend badgering the judge, if I don't meet that threshold of 500, it's still not going to let him go. Okay? So this is important because the fact that there is a minimum threshold, there's this energy that has to be met to get him out of jail. This is the same thing analogous to me being at the ground state. If I'm going to move from the ground state up to a higher energy state, I have to have a certain amount of energy. I can't go part way and hover, okay? I'm either here or I'm there. I can't be halfway in between. So Nathan is in a quantum state. He's either in jail or he's free, okay? There's nothing in between. He's either in jail or free at last, free at last. There's nothing in between. So if I show up with 490 and his jail was 500, his bail is $500, it's not going to happen no matter how long I plead. It's not going to happen. So this contradicted what was called the classical idea of this situation. They thought, like let's say for example, I shine red light on the surface. If I shine red light on the surface, and I know red light has a longer wavelength, and I don't detect a current, the thought process was that if I shine red light longer, it would begin to vibrate more and more and more and more and more, and eventually Nathan would get out of jail, or eventually the electron would go flying off. I just had to give it enough time. But what happened is that they never saw that happening. So either this happens right away or it doesn't. So, but here's where you can get into the weird thought process. So this simulation, which you're going to use for lab, is pretty cool, but it does have a little bit of limitations. So let me kind of show you how this works so when you get to this lab, you know what's going on. And it's a pretty decent simulation. So here's the setup that you have. So what you can adjust is two things. You can adjust the wavelength of the light from UV, being ultraviolet, which is higher than violet light, all the way down to IR, which is infrared, and then you have the visible spectrum in between. So you can adjust the energy of the photons that are striking the electrons, okay? You can also adjust the intensity of the light, okay? Now, so I'm going to move this, I'm going to start moving this over here like this, okay? And you can see the wavelength. So right now I'm at like 650, okay? So what's happening is that I'm shining this light on this metal. Electrons, if they happen, are going to get kicked out and they're going to go across like this. So this is Nathan stuck in jail. This is the McDonald's across the street. Colin going. Hey, buddy, we got McNuggets.
No, Arby's.
Arby's. Okay. There's Arby's over here with the Moz sticks, okay, and the marinara sauce, right? So, but Nathan's stuck in jail. So this is the red light would be like me showing up to get Nathan out of jail, and I got $490. Not going to happen. But if I want to increase the energy of the light striking the metal, do I make the wavelength shorter or do I make the wavelength longer? Shorter. So if I move this over here, we'll go to 568. Okay? So now we're in a green light / yellow light. Okay? Do I have any electrons moving up?
No.
No. Have I increased the energy?
Yes.
Yes. But I still haven't met that threshold. Okay? I might be like at $499. The judge is going, you're close. Still not going to do it.
Close.
Okay? But if I go to, say, 475. Now, this is where this fails miserably. You're not going to see these electrons going across. Okay? They showed this as a visual, as like these particles going across. It's not going to happen. You are not going to see these things going across at all. Okay? Just because the tiny little electrons are going across. So don't look at it as, oh, the photoelectric effect. We can see the electrons. No! Okay? Can't see it. So, but here's the point, is that if this happens, and it either happens or it doesn't. So if I move this back into that green zone, I still get some. But if I go even shorter, then I stop it. So what that means is there's a threshold. And either it happens or it doesn't. Okay? There's no, oh, if I give it enough time, it'll heat up and I'll start to see electrons coming out. But if I have it high enough energy, and I shift this over here to this, okay, into the 422 range. So now I've got these electrons going across. So this would be analogous to me showing up with $600. I got enough money to get him out of jail, and I've got some money left over. So in this equation, K max, and that's the kinetic energy, and you got to keep track of your ons in this equation. This HF is the energy of the electrons. The work function is how much energy it takes to free the electrons. So you got photons minus electrons. Okay? The leftover energy is how much the electrons are going to have. So this K max is, if you want to go with this analogy, this is how much money I'm going to give to Nathan after I get him out of jail so he can go move down the road. Get an Uber driver, go to Arby's, go to prom, whatever. Okay? It's like, yeah, that'd be really awkward. You call me tomorrow. Hey, Bert, I'm in jail. Jordan's going to kill me. I got to get to prom. Okay? So I'm going to show up, $600. Hey, out of jail. Here's a Hunsky. Go buy her some flowers. Take her out to dinner. Okay?
Might happen.
Might happen. So I swear to God, if you're in jail, you call me, I will not answer. So the K max is how much is left over. And that's reflected by the energy that the electrons have. So if this HF just equals the work function, then basically I could get Nathan out of jail, but he's stuck there. He doesn't have money for the Uber, for the Arby's, nothing. Okay? But the bigger this number is, the more energy that I carry into it, the more excess energy Nathan has to go out. Now, the problem is that's tough to measure. How do you measure the kinetic energy of a little electron? Oh, but they came up with a different way. So, what you have here is a battery, okay? That I can create a voltage across here using an external battery. This is the current that's flowing through the system. Not much, 0.055, okay? Now, a couple of things. I'm going to increase the intensity to 100%. I'm only at 58% now. If I increase the intensity to 100%, what do you think is going to happen to the current?
It's going to go up.
It's going to go up. Why?
Because there's more electrons.
It's a lot more movement.
Okay? So let's bump this up, right? So we're up to 96, our current goes up to like 0.09. So that would be like there's a whole bunch of Nathans in jail. All of you are in jail. And this is how many of me are showing up to get you out of jail. Okay? So the more of me show up to get you out of jail, more you're going to get out of jail. Okay? Which is shown by that current. Now, but however, even at 96%, if I decrease that into that green range and yellow range, even with an intensity of 96%,
No.
guess what?
No jail.
No jail. Can't get out of jail. So even if I shine it with a really intense light, because intensity is just how many of me are going to show up. So there's a whole bunch of us knocking at the door, but none of us have bail money.
You guys are congregating.
Okay? But if I shift this over, now we've got a current. Now the other thing that happens is that you're going to 0.118. So that's something you can hook up an ammeter and you can measure. 0.118 amps. But that's tough to then work backwards and go, well, how much energy does that actually have? So an interesting thing happens. Now I'm going to use the battery. So in this program, you can do three things. You can adjust the intensity, you can adjust the wavelength, and then you have a battery. So I'm going to shift this battery to a negative voltage. Now, you can't see it from back there. But when you do this, and you've got this negative voltage, this side over here is negatively charged, and that side over there is positively charged. So here's what's happening in terms of Nathan. I got Nathan out of jail,
And I want to go back.
but he's got protesters on the other side of the street going, no, get back in jail.
Yeah.
Okay? And then he's got his cellmates in the back there in the jail going, yo, Nathan, we love you, man. Don't leave us. Okay? So his homeboys back, that are used to 3 hots and a cot are going, wow, hey, Nathan, we want you back. So he's being repulsed by the protesters across the street, and he's being attracted by his cellmates.
Yeah.
So he's going to go. I get him out of jail, but he ain't leaving. He's going back. Okay? But an interesting thing happens. So what that tells me, this is what's called the stopping potential. Stopping potential is how much energy it takes to reduce the current to 0. So if I take this and slide this over a little bit, okay, now I'm down to like minus 1.2, okay? So I'm still stopping I'm kicking the electrons out, but I don't have a current. But Nathan's going further away. Protesters are getting a little weaker. The cellies aren't going as much. I go to,
Still no current.
that's tough.
Hey.
You should be able to like type this in, but I can't. Hold on.
He should have let him have this.
Bro, first temperature is like 40 years. Actually, yeah, you guys have no one.
Hey Nathan, what about this one, bro? Stop hating.
Okay, so I got it at negative 0.6 volts.
Oh, but the electrons are making it over.
But now my current, so here's the story. So if I know, like that current to stop it is negative 0.6, okay? I've still got a little bit of current, so I've got to figure to actually stop it is going to be a little bit more than that. So this is a measure of the electric field. So here's the story. If that's positively charged over there, and that's negatively charged over there, what's the direction of the electron field? That's negative. This is positive. Is the electron field pointing to the right, or is the electron field pointing to the left?
An electron field?
The electric field. The electric field
Is to the right.
is pointing to the right or pointing to the left? Right, because that's what a positive charge would feel, right?
Yeah.
So positive charges would be all about this. They'd be flying over there because they'd be repulsed by the positive and attracted to the negative. These are electrons. So it's very easy to adjust the voltage on this battery. So if I can find that threshold where I just stop the current, that will tell me an idea of how much energy the electrons had when they left the surface. Now, yes, ma'am.
How come some of them are moving faster than others?
Here's the best analogy that I can give you. So Nathan is in jail and he has like $500 to get bail. Gavin is in jail, but he's deeper. Okay? It takes like $1,000 to get him out of jail.
What did they do?
Okay?
Grand Theft Auto?
So this would be like me showing up with $1,200. So I got $1,200. I can get Nathan out of jail. That's going to cost $500. So Nathan's going to have a lot more energy to go. Gavin, I can get Gavin out of jail as well, but he's not going to have near as much energy. So the reason there's a difference is that these electrons are being pulled out from different energy levels within the atom. So the ones that leave with more energy are closer to the surface because they're not as attracted to the nucleus. Okay? The ones that leave with more because they lost more energy getting out from escaping the nucleus.
What's with the
Okay.
sodium? Top right says the target
Oh, yeah,
sodium.
there's different ones. We'll deal with that later. Okay. Now, an interesting thing happens. Now, I'm gonna move this thing back to 0 as best I can.
Golly.
Getting 100% resistance. You better hit with the people.
Okay. Let's assume that that's 0. Now I'm going to switch it over to a positive voltage. So if I switch it over to a positive voltage, what happens to the electrons?
Go fast.
Speed up.
They go faster. Why do they go faster as they go across? So now I've made this plate negatively charged.
Inmates want Nathan out of there.
Yeah, now they're kicking him
Yeah.
out. Okay? But an interesting thing happens. So that's at 2.6. So if I'm at 0.6, I got a current of 0.118. If I go to 1.8, I still have a current of 0.118.
Wait a minute.
If I go to 3.4
So
volts,
there's a
Why does the current stay the
maximum.
same?
I still have the exact same current.
I equals
Why
B
is it
over
the
R.
same, Barry?
So now, only thing that's happening is that I'm not opposing the flow. So all that's happening because of the fact that there's nothing pushing back, all I'm doing is taking the electrons and making them go faster as across. But it's still the same number of electrons that are being kicked out of the surface. So it's a number of electrons that are being kicked out of that surface that determine the current. So if you look at different metals, now, so let me go move this back to 0. Close enough. So I can change this to, like, say, calcium. Okay? Now, an interesting thing happens. If I change this to calcium,
Berg, why is that?
so look at this.
Oh.
Ah!
What was the first element?
So if
Sodium.
I'm at sodium, I have a current.
Oh, wait, I know.
Hold on.
Mr. Bergen,
Hold
can
on.
you explain it? I think I
Wait.
know.
Shh. Hold on.
I know you can.
Top and
If I'm at sodium, I have a current. So this is shining on the sodium. If I change that to calcium,
Yeah, I can explain this, Bergen.
why?
Okay, so sodium, really reactive on the left side.
No, you're making this.
No, there's an electron on the outside, only one though.
Okay.
And so it's not like, as close to the nucleus. Nucleus over here, electron over here. Electron is.
I think you're overcomplicating
I
it.
personally think all the time.
It's easier to take
Okay.
one electron.
Is there more valence and electrons?
It's easier to take one than.
Don't throw valence electrons into this discussion. Let's just make this simple. If you go back to this equation, that K max equals HF minus your work function.
This equation.
So I kept the same light, right?
Right?
What word did you use?
Yeah.
It got bigger.
Is that H4?
It increased.
No, that's
Frequency.
HF.
Okay.
Minus your work function. So Shaq, let's revisit your answer.
It got bigger.
It got what got bigger? The work function got
'Cause
bigger.
there's more.
So what that means, that would be like I show up and I'm thinking the bail was set at 500,
5,000.
but it's and now it's like 5,000. It's like, dude, now I can't get Nathan out of jail because the work function's gone up. Shannon.
Is work function intrinsic, or is it like a chemistry reason for why it increases?
No, there is a very much chemical reason for it.
It is. What do you
Okay,
think?
but
I can't hear, Shaq. What was your answer?
so there is very much a bond strength function to this. So the bigger this is, the more tightly bound those electrons are, the more energy it's going to take to get them out.
That's what I said.
Now, so here's the weird part of this, and this is why, and I had this discussion actually last night with a buddy of mine. The more you study quantum mechanics, the weirder it gets.
The less you understand.
No, it's so weird because if you look at this interaction, okay, I just visualize what's happening on an atomic level. So here's this tiny bit of matter that we call an electron, otherwise known as chihuahua. Okay? So here's this chihuahua. We don't even know where the chihuahua is. We know it has a certain amount of energy. We'll get into what's called the Heisenberg uncertainty principle later. So all we know is that the chihuahua has a certain amount of energy. We have a good idea of where it is, but we can't say with high degree of certainty. So here's this chihuahua moving around close to the speed of light, creating a chihuahua cloud. Okay? Now, along comes a photon, which is nothing more than a bundle of energy that has a specific wavelength to it. Okay? Now, you can kind of visualize it like this. So, here's this electron moving around. Okay? Rolling around close to the speed of light. Going around, going around, going around. All of a sudden, bam! Here comes this photon. So the photon has to interact with the electron.
Yep.
Okay?
That's kind of hard to do, isn't it?
That's the whole point of this. Okay? So this chihuahua is running around close to the speed of light.
It's like Shane.
This comes in, bam! Gives it enough energy. But here's the odd thing about the chihuahua. If this doesn't have enough energy, the chihuahua ignores it. So that'd be like the judge is saying, you don't have enough money, go away. I don't care what you're doing. So if this is going around, and this is this whole idea of quantum states. So this is going around. Cool. Right? Photon comes in, it's red light, doesn't have enough energy. But if I hit it with a blue light photon, bam! Then I give it enough energy to not only make it move to a higher energy state, I make it go away. Like this thing completely leaves the nucleus. Free at last, free at last. Good God Almighty, it is free at last. But that chihuahua will not interact with the red light because it doesn't have enough energy. But it'll interact with the blue light. It'll interact with it. It'll give enough energy. The electron says to the nucleus, deuces, I'm out. And it's gone. So this is somewhat analogous to what potentially happens, say, at prom on Saturday night. So you're chilling out with your date. Certain amount of energy, there's a certain amount of attractive force between the two of you. Okay? And someone comes up and says, hey, let's go. Okay? But you're going, no, I'm attracted to my date. I'm going to stick with my date. Okay? But if someone comes in and says, look, I will give you $5,000 right now to leave your date. See you, babe. I'm out.
Yep.
Okay?
Gavin's
Gavin's like, I'm going to get left behind.
Well, what's the minimum?
So, but that's what you have to figure out. And that's what we call the work function. All right. Now, if you look, I gotta find this on, now we're gonna jump ahead to chapter 28.
Jack, are you going? What about Africa?
I don't know. I'm a student.
I have Easter.
I didn't know.
What?
My parents have Easter that day.
Okay.
My family has Easter that day. I can't go.
It's just that.
I have Easter tomorrow.
Is it like Jewish Easter or something?
No, not even
My
Jewish
family
Easter.
is
Saturday.
Jewish.
It's Saturday
Jewish
night.
Easter.
I had to take off work for it. I can't.
Okay, so basically Jewish.
Okay.
Easter is.
Wait,
Hey, I think we should focus on the teacher.
Okay. So on page 913,
oh, I'm there.
there is a table that lists the different work functions.
Whoa, nice.
From potassium all the way up to gold. Gold has one of the higher work functions. So what that means is that that holds onto its electrons a lot more than the other elements do.
Yep.
So over here, your book lists this a little bit different. They say K max equals E of the electron minus E naught. Okay, which is kind of a weird way to do it. So this is why it's more functional to say that's HF minus the work function. So notice that these are in electron volts. So what this means is if you want to generate the electron or the photoelectric effect, say for gold, the energy of the photons has to exceed 5.10 electron volts, which would require a really, really short wavelength of light to get gold to have the photoelectric effect. Potassium, much lower, okay? So potassium has a much lower work function, so it's much easier to get electrons away from a potassium atom than it is away from a gold atom. Okay. All right.
Where did it go?
No, it's not.
Is it like Hanukkah basically?
Hey, let me see. My family just Easter. It's really hard.
Wait, so you're
Because I usually close every Saturday night. And my family doesn't know how to accurately time things ahead of time. So I miss like multiple family gatherings.
Where do you work at, Shaq?
Where do you work, Freddie?
He's always surprised.
Yeah.
He works in a bank. They make
Yeah, he works at a bank in Tel Aviv.
They make you can't take off days more than 2 weeks. And it has to be more than
So
2
is
weeks.
your family coming from Tel Aviv? Is that why it's taking?
No, my family's just lazy, Evan.
What?
It's also my stepmother's birthday and my great grandmother.
That's
Yeah.
okay.
So did you guys not do? Did your family not do Easter?
So what
They
rituals do you
saved it
guys
for
do?
you.
That's
devious, not really.
Because I'm available Sunday. So I don't know why we're doing it now.
So Shaq, what rituals do you guys do?
Rituals. Does an egg hunt count as a ritual? I mean, it'll be at 6 o'clock at night.
What do you want to say?
No, it's not.
But I don't think I can convince my father not to go to Easter. So.
Does it cost too much?
Bro.
Answer why.
Nathan, you know that's
What?
all on video, right?
Oh. Mike,
So,
Oh dear.
when you get to question number 9, if you look in the answer, the back of the book, the answer is horribly wrong. Okay. Okay, so don't flip out and you go, I got a completely different answer. That's because the answer is wrong.
Bro, how do they mess it up?
I never used the back of the book.
Did they just
for-
mess it up?
Usually references in the back of the book.
I was joking. I never used the
Now,
back of the book.
do not go to ChatGPT and use different work functions.
What does that
You
mean?
use the work functions that are in this book. This is what I base this answer key on,
Uh-oh.
right? So do not go to some other source and look for work functions,
Dang.
okay?
Yeah, but we kind of don't use AI.